In this lesson, we will be exploring function notation, and we will be using function notation to evaluate functions, perform operations on functions, and solve problems. So the easiest way to understand function notation is to think of the machine concept. The machine concept helps us understand how a function works. The values of the input, which are x values, which we know represent the domain, because domain are all the possible values for x, are fed into the machine, so into the function f at x, to produce the values of the output, the y values, which represents our range, all the possible values for y. Function notation, which is that representation f x. F at x is used to represent the value of the dependent variable y for a given value of the independent variable x. F at x is read as f at x or f of x. Note the symbol f at x is just another way or another name for y and represents the value of the function at x. That is, notations y and f at x are interchangeable. They represent the same thing. So y is equal to f at x. Example, if you're given the equation y is equal to 2x plus 3, it is the exact same thing as f at x is equal to 2x plus 3. Sometimes we use g at x, h at x. Scientists and mathematicians will sometimes use a letter related to the quantity being measured. So for an instance, you might have a word problem where you see h at t as height being measured as a function of time. So let's look at this function machine. We have our input, which is x, that we're going to put into our function, which is represented by x squared, and our output, f at x, is going to be 9. Let's test that. We are given the function f at x is equal to x squared. Our input is 3, so instead of x, I can replace it with 3. Now we want to figure out what that output is. So we're going to substitute where we see x. We are going to replace it with 3. And then we're going to simplify. 3 to the power of 2 we know is 9, just as the function machine stated. So in simple ways, f at x equals x squared. If I put the input of 3 into that function, my output would be 9. So f at 3 is equal to 9, or we can say when x is 3, y is 9. Okay, let's try another example. We have the input, which is 25, and the function given is 2 times the square root of x plus 1. Given the function f at x is equal to 2 times the square root of x plus 1. The input is 25. So where I see x, I'm going to replace it with 25. And simplify. Keep in mind we are always following BEDMAS. So we would work with simplifying first. What is the square root of 25? Well, the square root of 25 is simply 5 plus 1. Right? So further simplifying, we'd say f at 25 is equal to 10 plus 1. F at 25 is equal to 11. So that means when the input was 25, the output was 11. Okay, let's evaluate some functions. Based on the graph given, y equals f at x, determine the following. So as we mentioned earlier, f at negative 3 is telling me the input is negative 3. I want to know what the output is. What is the corresponding y value? So we'd look at the graph and we'd go to x being negative 3. So if we see here, when x is negative 3, what is the corresponding y value? So when x is -3, the y value is 0. Okay, at B, it's asking us when x is equal to -2, so our input, what is the corresponding output? So going to x equals -2, following all down here, we can see that the output is -5. F at -2. So when x is 2, what is the corresponding y value? We can say the corresponding y value is 1. D is tricking us. We have f at x is equal to -6. So now it's telling us y is equal to -6. What is the corresponding input? At what value of x on f at x is the y value -6? So we go down to -6 for y and figure out what is that corresponding x value. And as you can see, x is equal to 4. So f at 4 is equal to -6. Moving on to example 2, this time we're given the function f at x is equal to 3x plus 1, and we're asked to find f at 3. So again, x is equal to 3. We put it into our function to figure out what is the corresponding output, our y value. So given f at 3, we're going to say 3 times 3 plus 1. So f at 3, always following BEDMAS. So we would multiply before we add. 3 times 3, which is 9, plus 1. F at 3 is equal to 10. So again, if I wanted to express that as an ordered pair, when x is 3, y is 10. Now for B, f at -3. So what would that be? In our function, wherever we see x, we would replace it with -3 and then simplify. So f at -3 is equal to 3 times -3, always in BEDMAS, multiply before adding. So -9 plus your 1, f at -3 is equal to -8. Okay, so f at -3 is equal to -8. So meaning when the input is -3 and we put that into our function, our output is -8. So as an ordered pair, that would be -3 and -8. C, a little bit trickier. We have f at 6 minus f at 2. Keep in mind, f at 6 minus f at 2 is not equal to f at 4. Okay? We are to simplify for what f at 6 is and then subtract that to what f at 2 is. So what I suggest is that we do it separately. Let's figure out what is f at 6. Meaning, when the input is 6, what is my output? So we're going to take 3 times 6 plus 1. F at 6 is equal to 3 times 6 is 18 plus 1. F at 6 is equal to 19. We will determine now what f at 2 is. So f at 2 is equal to 3. Again, when our input is 2, what is the corresponding output? F at 2 is equal to 6 plus 1. F at 2 is equal to 7. Now we can determine what f at 6 minus f at 2 would be. F at 6 minus f at 2 is equal to 19 minus 7, which is equal to 12. Okay, example number 3. If f at x is equal to 5x plus 2, determine x if f at x is equal to 12. So again, now we're given the function, but we're given the output. We are trying to find what is the corresponding input. So starting with our equation, we have f at x is equal to 5x plus 2. Well, we were given that f at x is equal to 12. So instead of f at x, we can replace that with the value of 12. So 12 is equal to f at x plus 2. We need to isolate for x, so we're going to bring over that positive 2, keeping in mind when you move from one side of the equation to the other, you change your operation. So this would be 12 minus 2 is equal to 5x. 12 minus 2 we know is 10. 10 is equal to 5x. Now, in order to isolate for x, we need to get rid of that coefficient up front, the numerical coefficient. If we divide one side by 5, we have to do the exact same thing to the opposite side. 10 divided by 5 is 2, which is equal to x. So therefore, f at 2 is equal to 12. The value of x is equal to 2 when the output is 12. X would be the input. And that was our unknown. Okay, moving on to example 4, we have the temperature of the water at the surface of a deep lake is 22 degrees Celsius on a warm summer's day. As Ronaldo scuba dives to the depth of the lake, he finds that the temperature decreases by 1.5 degrees Celsius for every 8 meters he descends. In A, we'd like to model the water temperature at any depth using function notation. B, we're going to use the function to determine the water temperature at a depth of 40 meters. C, at the bottom of the lake, the temperature is 5.5 degrees Celsius. How deep is the lake? So before we can do anything, we do need to come up with what function would represent this situation. So we have that we start. So we need to start defining variables. And as mentioned in the beginning of the lesson, when you're determining functions, sometimes you want to incorporate the measures being what we're trying to look for. So in this case, we're looking to do depth. So a good variable to use, and we also are looking at the temperature at those depths. So a good variable to use would be T for temperature and D for depth. So when we're modeling, we're going to come up with, of course, let statements. We're going to say let D represent the depth below surface, and we're going to let, so that's our input, our independent variable, and we are going to then express T at D, our function, to represent our output, the temperature at depth D. Okay, so we're given that, and I'm going to highlight that. So it's really important to summarize what information we have and what we need to figure out. So we're given that, the temperature decreases 1.5 degrees Celsius, for every 88 meters. Okay, so we also are given that the water at the surface of a deep lake is 22 degrees Celsius. That means we start at 22 degrees Celsius, and then the temperature decreases 1.5 centimeters for every meter he descends. So if we were to look at that, we need to figure out that rate at which it is changing the temperature according to the depth. So we're going to figure out that rate of change. So we're going to take 1.5 degrees Celsius every 8 meters. Using our calculators, 1.5 divided by 8. And the rate of change there, 875 Celsius every meter. Okay, and that'll help us come up with the actual function. We are trying to figure out the temperature at a certain depth. We know the initial temperature, which is 22 degrees Celsius, minus, actually, we don't have to use the units. In the end, we want to make sure with our word problem. And then it decreases 1875 right, every meter. So there we go. The function that will model our situation. Keeping in mind, 22 was the initial temperature. And then rate of change, that is, we lose 0.1875 degrees Celsius each meter. Okay, so now we're going to use this information or this function that we determined to determine the water temperature at a depth of 40 meters. So we want to know what is T at D when D is equal to 40. Okay, so given the function, again, we want to know what the output is when the input is 40. So with that in mind, we are given the function T at 40 is going to equal to 22 minus 0.875. Instead of D, we can replace that with 40. Okay, so keeping in mind, we always want to follow BEDMAS. So we're going to take 0.1875 times 40. And T at 40 is equal to 22 minus 7.5. Well, T at 40 then is equal to 22 minus 7.5, which is 14.5 degrees Celsius. And this is where we want to bring back our units. And because it is a word problem, we want to answer that question. It says use the function to determine the water temperature at a depth of 40 meters. Therefore, the temperature for the water temperature at a depth of 40 meters is 14.5 degrees Celsius. Now, this time in C, it says at the bottom of the lake, the temperature is 5.5 degrees Celsius. How deep is the lake? So this time, we're given the output. We need to figure out what is the input. So we are given T at D is equal to, what do we say, 5.5. We need to figure out what is D. Okay, so again, we've highlighted the function. So we're going to use that function to figure out what is the input given that the output is 5.5. So we can say, therefore, 5.5 is equal to 22 minus 0.1875 D. Now we have to solve for D. So we're going to bring over the 22. Keeping in mind, when you bring something from one side of the equation to the other, you want to make sure to change the operation. So it's going to be 5.5 minus 22 is equal to negative 0.1875 D. 5.5 minus 22, we're at negative 16.5 is equal to negative 0.1875 D. We want to isolate for D, so we're going to make sure to Move that around so we can see what's going on. Divide that by negative 0.1875, negative 0.1875. A reminder again, what you do to one side of the equation, you have to make sure to do to the other. Divide that by 0.1875, and we're left with 88 is equal to D. Right? So again, answering the question, how deep is the lake? Therefore, the water temperature at a depth of 88 meters is 5.5 degrees Celsius.